So for now, because the recording started, we were switched off the videos, but feel free to put on the video if you want. And it's really great pleasure for us to. It's a great pleasure for us to host the lecture by Francesco Vaccarino, who is a professor from University of Torino, who will talk to us about the topological constraints in shallow ReLU neural networks. Yeah, it would be great to speak with you in person, of course, but for now it will be in virtual. We will try to handle all their Teams meeting obstacles. And feel free to unmute yourself because I made you a presenter and you will be able to, I hope you will be able to share also the slides. Yeah.
Hello, everyone.
Yeah, great.
I'm able. I probably found a way which I forgot before. Anyway, my name is Vaccarino Francesco, as Luba said, and I'm from Torino. I'm from Politecnico di Torino. By education, I am a mathematician. In the first year of my professional life, I was working mainly on quite abstract things like representation theory of algebraic groups in positive characteristic, just to not leave anything out. And then for a period, I work in industry. Then I come back in academy in 2007 after 10 years outside. And now I'm here, and in starting maybe around 2010, 2009, I started being interested in topological data analysis and then in machine learning. Currently, I am teaching, as an example, mathematics for machine learning and mathematics for artificial intelligence. And also I have a course in topological and geometrical aspect of machine learning in my university, which is depends on the scale. It's a quite big one. We have 40,000 students, so it's a big university. And so today, thanks to the invitation of Luba and the organizer, I will share with you some work that we have done together with two people that probably are connected. I see both. Pierrick is here. Ciao, Pierrick. And I have seen also Marco, but now I don't see it anymore. No, it's there. It's there. Okay, with it's a joint work with Marco Nurisso and Pierrick Leroy. And is a work that has been accepted and now is practically published. It's not clear to me the mechanism of publishing of no RIPS, but in any case, we are accepted and is on the website in open review. You can appreciate the long discussion with the 5 referees. It was quite tough to do this. Anyway, so now let's try to start some kind of experiment in which I will try to solve the problem that I have so far in, come si dice? I have to, if I speak and try to do something, I never do it. 1 second. Here.
Take your time. And by the way, yes, by the way, if there will be some questions, will it be okay for you that we ask you during the talk? Because
yes, don't worry.
Maybe some clarification.
The only problem is that I'm a sort of divagator by myself. So if you okay. So now we make it this way. Look at this. Huh? Share. 1 second. Okay, 5. Ok, ce l'ho fatta. We made it. So, look, and then share.
A small excursus to Italian language. That's great.
No, but it's working. At the end, it's working perfectly because I remember the trick we made during the COVID before using all the modern version of these things. So I think now you see me and you see also something, right?
Yes, perfect. Perfect.
Yes, you know the
Beautiful.
trick? The trick is called QuickTime. I'm registering my iPad with QuickTime, and QuickTime is inside the computer, so the teams can see it. Because with Zoom you can link directly. Anyway, thank you. This is the first slide, and as the title says, we are going to analyze topological obstacle in training shallow ReLU neural network. This things has been already a little bit improved for more complicated network, but for the moment we start with this. So what is the idea? What is the objective? The objective is to understand training dynamics in neural network. This is clearly something of paramount importance in any kind of operation with neural network, understanding what happened along the path by means of which you train the network, which usually is based on so-called empirical risk minimization. So practically, you try to find the minima of the loss once you fix some training data. So one of the questions might be this, for us was the key one: how do topological features constrain optimization? Plainly speaking, as an example, one point is the following: if the landscape or the domain, to be more precise, of the loss is disconnected, it may happen that there are points that are not reachable starting from one connected component and going to another. So what we try to do with this kind of objectives, to which kind of network, which kind of architecture we study a very simple one. This is called Shallow ReLU. I assume that 90% of the people know this, but nevertheless, I would like to spend a few words on, sorry, I want to move this, okay. Few words on this. So usually we are used to see network represented by graphs and so on, but actually this is nothing but a composition of function. It's only represented graphically because it's nice. Even people, I met people, I taught in a very funny and interesting master, specializing master for journalists, for communication of science. And I tried to explain them this, and they were convinced that this is a sort of physical device. It is really, you know, neuron are something, are circuit, and it was difficult to make them understand that this is nothing but a graphical representation. It's not actually a physical connection. In any case, for those ones that are not completely aware, and also for myself, so I remember everything, the ingredient of this game are follow. No, so you practically have two functions. The first one is this sigma W1 that we describe, and the second is W2. So W2 simply is a matrix. Okay, is the matrix whose entries are physically represented by the edges here in this zone. Let me do a little thing so I can use the pointer. Is this one? Yes. Okay. Is the pointer? Yes. Okay. So this guy here, all these edges represent simply multiply times a number. And so we can collect all these edges stuff practically as matrices with entries and multiplication and sum. Then inside, for the moment, and in this case, for this case that we study, here inside of the neuron, you have activation function. We assume is the same in the layer, in all neurons, so-called neuron, and this function is the ReLU. So in the paper we wrote, there is a more general thing. You can use a so-called homogeneous function, but for the moment, let's stick on the ReLU. Then if one can go to the paper and read all the general detail. But for the moment, imagine this ReLU. So people, this is the stupidest network. Let me say, it's the basic, super basic network. There's nothing simpler than this. In network neural network theory is called shallow because there is only one hidden. Nevertheless, the theorem say that you can represent practically any function by using this if you take enough neuron, but it's impractical. Okay. one very important thing.
And can I ask you
yes,
a very, very stupid, also very shallow
so
question?
it will be difficult to answer.
But because you say that, I mean, it's unpractical, probably, right? Because it's shallow, right? Because it's kind of like it would require. This is one of the reasons, right, why people kind of, right, usually would not use it typically.
Yes.
Mm-hmm. Yeah.
Yes, it's impractical because practically you find yourself with a hidden layer with 1 zillion of neurons, and you have only two matrices which have a very, 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 very low rank, and so it's difficult to compute practically. You have also problem of sparsity. Spreading the information on more layers using deep neural network allow you to at least try to control this problem. Okay.
Mm-hmm.
Okay, thanks for asking. Thanks for asking. And now, something that is clear to anyone working in science, mathematics, physics, whatever, is that when you have anything which is defined up to something, up to some symmetry, you have on one side an information, on the other side a problem. Because if you don't take into account this, you are producing observable that are you have a problem of so-called identifiability. Okay, so if you have a quantity which depends on the parameterization of the network, as an example, or whatever it is a general concept, you have a problem if this quantity is not clarified with respect to this. And so therefore it's very interesting to try to understand which kind of symmetries are natural in such a kind of network. And in general, the term which we borrowed from a paper of Benjo in 2017 is this observational equivalence. Observational equivalence means that if I go into the parameter space here, okay, let me wait 1 second, only one thing, sorry. I changed the color, okay. You have the parameter spaces. No, this is the first layer of parameter, the second layer of parameter. Imagine you have a map phi here from W to W such that the resulting function, the resulting neural network, once you compute in a point, has the same value. So you change the parameter, but you get the same value. Let's give immediately an example, which is an example of paramount importance because for us, because it's the one we developed. Neuron rescaling. You take a single neuron here in the middle, one of this guy, okay? And then you multiply all the entry weight times alpha positive. And then you divide all the exiting weight by alpha minus 1, the same, okay? Alpha minus 1, positive. Then by aggregate...
Francesco,
yes?
just a clarifying question. Here you talk about the any neuron, right? Here it's not. It's important for you, right? That it's it is the one which is taken from the
inner. Is the inner. Yes.
Yeah, the inner one. Yes. So
yeah,
it's
here.
Only from this layer.
One of these. Each one of these, you can take all these edges that enter and multiply times alpha, and take all the edges that go out, you divide by alpha. Okay? And you can do it for each neuron with a different alpha, because it's something that is defined neuron-wise. Here is defined for a single neuron, and then you replicate it for all of them. And there are reasons, the reason is that you make some computation, you see it works. And that by aggregating this, you have an action on the entire network in the sense that now you take a matrix, which is diagonal here, and this matrix diagonal has alpha 1, alpha n, where each one of these correspond to one neuron, one hidden neuron, and you have a set of parameter of the network. And you have this operator T alpha, which is multiplying rows of this by alpha, which correspond exactly of doing this. Okay, this guy here is this, and this guy here is this. But since it's neuron-wise, it's a diagonal action. You put all together, okay? The various neurons have no common edges, so you can do it independently for each one of them. And then you aggregate, you pack the things, And then you use this property, which is exactly this related to the fact that ReLU is homogeneous. So the fact that if alpha is positive, and you put multiply times alpha the argument of a ReLU, then alpha pop up. You get the same function multiplied by alpha. So it's a sort of linearity property, but it holds only for positive alpha. If alpha is 0, you kill the ReLU, and if alpha is negative, it doesn't work, okay? Because it changed the sign. Since the ReLU, if it is positive, is the object. If you multiply by alpha, alpha is positive, and z is positive, you get alpha z. If z was negative, and you multiply by alpha, which is positive, it remains negative, it remains 0. So it's the same of doing this. And this means that in this action that we have just defined, you can take the alpha out of the action somehow, it jump out of the ReLU. And so it results in this thing, that if you multiply left and right by this sort of rescaling operation, each neuron independently by this alpha, each one for his own alpha, then what you obtain is observationally equivalent to the initial network. So it means that if you rescale the inner neuron, each one by an arbitrary positive number, the function you obtain out of the network is the same. Practically, it's the same function. It's simply written in another way. Is let me say, just to clarify, it's like you write this: f of x is x. And then the transformed T alpha of f of x is 2 times f of x divided by 2. So you are doing nothing, practically. This is the game. So you say, who cares? I have no room and no time of doing this. What is the motivation of studying this operation? Is that although the network doesn't change as a function, so is observational equivalent to the previous one, what you obtain is that both the gradient and the Hessian of the loss change. Because if you apply standard calculus and chain rule, and you compose with this action of T alpha here, you will find yourself in a situation in which this quantity change. And Benjamin in that paper was observing that this hinder completely some observation on the goodness of minima, as an example. Saying the minima is flat, epsilon flatness, epsilon sharpness, spectral radius of the Hessian, all these things are ill-defined. Ill-defined because depends on the parameterization you choose. But our task is not this. This is one, let me say, motivating and inspiring thing, but it's not what we were working on. There is also another action at hand, which is a permutation, but I skip it for the sake of time and simplicity, okay? But it's the more complicated is this one. Okay, nice. So here we have this nice two action, as I see before. And here, drawn in light blue, here in turquoise, you have this orbit, okay? These are the orbit under the action. So imagine you have, this is a plane which is a sort of a cartoon, because W1, W2 are high dimensional, no? But you see this curve here, you imagine these are the orbit under the action of T. Alpha change, and you take your parameter of the network and you move it along this orbit by using this rescaling operation. Okay? So what happened? It happened then, thanks to this observation here, we have a very interesting fact. We have the fact that the function, when you use this action, the function remain constant. So this tell us something about the loss. Also, the loss remain constant, doesn't change, because the loss is based on the function as its own pieces. But once you fix the point, once you fix x, and you compute the loss of theta or w, call it as you like, in a certain configuration, then since these two are the same, it means that the loss computed in W is the same as the loss computed in T alpha of W. Indeed, I'm writing this here. Some notation. I take the training, This is a training set. With this notation here, I mean that as usual, I'm presuming that I'm picking up my data, I'm drawing data in a IID fashion from an unknown distribution. Okay. Probably I've written something which is not correct. Sorry, correct. I see something I don't like. Here is M, because D is the dimension of the space, M is the number of the samples. Okay. Now, here I have a loss, you see, the loss, but this loss is unspecified for the moment. So what I do, I fix a training set, I train my network, and I compute the loss. I do not go into detail of this, whatever it works. How do usually I do this? There are various techniques, more or less complicated. One of the basic is the so-called gradient of steepest descent. So we go down in the direction opposite of the gradient, and we update the weights accordingly. Now, this is the standard little game we play with this, and this is called gradient descent. Now we replace this with something typical from analysis and mathematical physics. What? Gradient flow. What does it mean? We replace this construction with a sort of continuous analogous. The idea is the following. We try to build a curve. We build a curve, W, or we assume we have a curve, because we don't want to solve. We are not working in solving the problem of finding the minima and so on. We are trying to understand what is the geometry of the topology of the set that you travel, in which you travel when you do this operation. Okay, so the question is like, when I'm going around making this training, where I am constrained to remain over a certain manifold, or I can wander around like I want, no? Because the idea maybe can be that, or maybe not. So some notation standard here, we denote with W dot the derivative with respect to T. T is the parameter, even if I didn't write it. So this is a curve. So imagine you have a curve was in the parameter space, no? And here you have a gradient field. In each point of the parameter space, you can compute the gradient of the loss in that point fixed x. X is fixed. X is fixed. Okay, so what we want to do is to study the solution of this equation, taking W dot T, so the derivative of W equal to minus the gradient of L computed in that point. Just to show you, if I remember well, if I'm not okay, noise here, we can see in this fantastic draw made by my young colleague, what is the point? So here you have a curve, see the red curve, and you are studying some, you are doing this gradient flow, and what you want is that this vector here, the tangent to the curve, is in the coincide with the gradient of the loss in that point. This is what is called a gradient flow. You have a gradient field and you have a curve which is an integral of the flow of the field. So observation, as I told you before, is rather trivial. Since f is constant on the orbit, also L is constant on the orbit of T. T is there is scaling. Let me call T as there is scaling, okay? So this means that what? This means that the gradient of the loss is orthogonal to the orbit. It's orthogonal to the orbit because the orbit is contained into a level curve or level set of the function in a zone where the function is constant. So automatically you have this. So now what happened? It happened that you can translate this fact in some in terms of polynomials, and that's nice. So first of all, we define a bilinear form here, which actually is not, in this case, is not bilinear. I cut something because it was too long. In any case, consider this quantity. Look at this. Try to understand what is this. if you see, in my opinion, it's easier to see in this way. What is this?
Which quantity? Sorry, Francesco. Which quantity you are referring to? The one which you defined is WWK.
Yes. I'm here. I take WWK, and I define this as this difference of sum of squares. You see it? Oh, it's okay. I don't understand.
Yeah.
And a way of seeing it, which in my opinion is easier, is this. If you take EK is the vector having 0 everywhere and 1 in one position, okay? Okay. Then what you can do, if you multiply this by W1, you obtain as a row, you take it as a row, times W1, you obtain a vector which is a row, and this vector is practically the kth row of W1. So it's W1 K1, 1, W1 K2, 1, and so on, okay? And here, the same, you get a column, the kth column. These two vectors, the kth row and the kth column, are the two guys. Which one? Look, I go back, pay attention. These two guys, row and columns, are exactly this guy here. The guy that enter into a vector in this way and go out in this way. So this corresponds to the row of W1, K row, the row 2 as an example, and this guy here are the element of the column 2 of W2. You can see it maybe even better in this little picture here for the scaling. So practically this guy here is EK times W1 transposed, and the guy here are given by W2 times EK. What is this about? What is this about? What is this equation? This equation is about this formula. It's about measuring the balance of what enters into the neuron and what goes out. These things here is the norm of the vector of weights entering into the neuron, this guy here. And this guy here is the square of the norm of the edges going out of the neuron. So these things that we have seen before, with some computation, non completely trivial, but not super difficult, give us the following result. That if you take the derivative with respect to t of this quantity, this difference, it is 0 when W is a gradient flow. So if W is in this way, is a gradient flow, then when you compute the derivative of all this quantity, all the derivative of all of these are 0, so which means what? They remain constant during the gradient flow, so during the training. So we have seen practically that using this decomposition neuron wire, using the fact that we have an action by means of which we obtain observationally equivalent things. These imply orthogonality of the gradient of the loss to the orbit. And after this, making some computation, you have this sort of conservation law. Let me write it here. These things, you can see it as what? The fact that theta, che, oh sorry, perché ho scritto theta? Lo so io perché non... W, K is equal to CK in R for K from 1 to N. This quantity do not change along the gradient flow, because the derivative of this form here is 0. So it means it is constant. So whatever you choose as initialization, you will have, so invariants are coming as written here. Since you have this, you can initialize the flow with W0, any W0. Then to W0, it corresponds a string of numbers, one for each neuron. This label you compute by using this form here. And this vector remain unchanged along the training. There is no way of changing this. Then it makes sense, considering all the things we are interested in, it makes sense to consider this invariant set. The invariant set is the set of weights having the same C vector. And it is clear that if you start from any W here, and then you are this way, and then you do a gradient flow, you remain completely prisoner inside of HC. You cannot go around. You can go around, but only into HC. So at this point, it may and this HC form a partition of the space. A point is in one and only one HC. So what is interesting to understand is to understand that these AC, how they are made. Let me go somehow directly to a part here, sorry. But I don't remember how much time I have.
You have time until at least you have at least 12 more minutes, but we can okay. Yeah, we can, if some questions maybe start before. Because
practically the point here is this. Let me try to do let me say go to the point. Then I have, if you like, I have some mathematical detail to understand why things are doing this kind of transformation and why not. Okay. So topology of the invariant set. First, we have this warning, maths ahead I wrote. So I have that W is can be written, so the entire space can be written as a product of spaces, and these spaces are made by, you imagine that W is made by pairs, no? And each pair is a element in the pair is a matrix. So here, if you have here, this is a matrix. In particular, this one will be N times D, and this one will be E times N, okay? Then what happened? It happened that you can decompose the space in pieces by making some little computation, and this is makes sense because practically at the end the entire neural network here can be decomposed as the sum of smaller neural network neuron-wise. So this justifies also the fact fully the fact that we work neuron-wise. Now, instead of I skip this, sorry, and I go directly, I write it by myself. Now, sorry, I have to do something like this. Okay. Okay. First, proposition one. In a shallow ReLU neural network, the invariant set I told you before, so the invariant set HC is technically is homeomorphic, but I write it in this way, okay? Homeomorphic to a product QC1 QCN of quadrics, and this is practically a rephrasing, because this guy here, any of these Q of CK is nothing but the set of U belonging to the WK that I decomposed before, such that UK is equal to CK. And since the equation is of this form, you have something like UI square minus UJ square equal to CK. This is the equation of a quadric. It's a polynomial of degree 2. and homogeneous. A nice one. But we have something more. So this is the first fact. The second fact is this. Second fact, proposition 2. If Ck is greater than 0, then Q of Ck, so this one of these pieces, is a topological manifold. So it means it's something nice, something locally homeomorphic to Rn or something like this, and it is homeomorphic to R to the E times Sd minus 1 if Ck is less than 0, then same things, QCK is a top manifold, but this time is homeomorphic to Rd times Se minus 1. D is the input, E is the output, just to see. If Ck is 0, then Q of 0 is contractible. Actually is something like this, is a cone, and you can contract it to the vertex. So here I have a nice picture again done by my friend, which is here. So you see, as an example, this is Ck greater than 0, the red one, and Ck less than 0 with the blue one. I'm a little bit cheating because this is the case in which E is equal to 1, okay? But nevertheless, the idea is that, you see, there are cases in which you have a connected things, you can walk around and try to look for your minima. But there are cases in which, according to the sign of this Ck, so practically, if Ck is positive, you have never problem. If Ck is negative, under certain condition on the dimension of the input and the output, you have that your space disconnect. So when you are looking to your weight, you are here, you are going around. No? You start and you start looking for your weight. You can do what you want here, but you will, and the minima is here. And you cannot go there. But we have symmetries, and I conclude with this, with the symmetries. And with symmetries, we can do what? We can do this. You start, you are looking for a good one or a bad one. It depends what you want to do. You are looking for something that is in another component. So if you go around here like this, although you will never be able to go in the right place because it's inside of another place, okay? But using the symmetries, the rescaling, you can always rescale your path so that you go into the right component. So practically rescaling can be used to go in the right component, or an unwise description, not description, sorry, an unwise computation, initialization of the network can create problem. In the appendix of the paper, now is long to show, we have also computed the probability to find yourself into this situation. So practically, to summarize, we have the following. Let me put it down in this way, just to wait a second, because I have done some mess to my things here. Wait, I'm arriving. Eccolo. Okay, here we are. So at the end, we have this result. So theorem. Same hypothesis, I don't repeat, so we have ReLU, etc., etc. Then the number of connected components in HC. So the number of pieces, disconnected pieces of AC is 1 if both input and output are more than 1 as a dimension. So in general, if you have a shallow with a number greater than 1 of input or output, the domain of the loss is connected. But if you have, let me do only one case, the E equal to 1. If E is equal to 1 and D is greater than 1, so you have some number of input, you have output is a single one. This is a typical situation. It's not so strange. It's the classical case in you have a regression with a single output, or in the case you have a binary classification as an example. So it's not so weird. In this case that I just said, you have 2 to the L minus component, and I write all L plus, and then you have L plus plus L minus. I tell you what is L plus, L minus. This is L plus is E greater than 1, D equal to 1, and this is E equal to D equal to 1. So L plus is simply the number. L plus is the cardinality of the set of K such that Ck is greater than 0. And L minus obviously is the same, but for less than 0. You have this. So practically, just to close, I want to finish with this, what we have seen. We have seen that if you want to train a network and represent the process in the following way, the theta, sorry, sometimes people, the letter start walking in my head. So, okay, is equal to this. Then, if you choose initialization, W, initialize, associated to this, you have this set of numbers, W, W, K, which correspond to neurons, okay? Is neuron wafings. This is the hidden layer size, and this thing usually we write like CK. They do not change along this thing, along W of T, the solution of this, and this implies that W of T is contained into HC, which is connected or not, depending on the sign of CK and the input / output dimension. We have also made experimental check and other things, but is everything in the paper. I think I can stop, and I hope you, if you have any question, I would be happy to answer. Thank you for your attention.
Wow, great. That was really a lot of interesting facts and beautiful facts. And if you can still keep the sharing of the screen, that would be great.
Yeah.
Because
no problem.
I think that it would be,
Yes, we can go back and forth if we need.
Yes, we can. If we can indeed.
Number.
Yes, because I don't know if there are already some questions in the audience about that, because I really liked how you kind of put this into the topological language, right? Of the fact of this kind of homogeneous ReLU nature, right? Into like translating that into the language of the space that you have. But do you then have the same possibility to explore non-shallow cases? I mean, it's maybe a naive question, but what is that you have, because you started with this model of neuron, right, that you showed with this W1, W2, and that makes it easy to study, relatively easy to study the shallow ReLU, but
but the point is that also for non-shallow ReLU, it turns out that the key point is this guy, is understanding how this work. And indeed, we have a result in general. And if my colleague let me, I share the result. So Marco and
maybe
Pierrick.
Marco can connect.
Do you agree? I want to explain this a little bit because we didn't publish this yet. But I think is okay.
If you want, we can, maybe what we can do is that we can stop the recording in any case for making people.
Yes, I would appreciate it. Yes.
So we can stop.
Nice.
We can stop the recording.
I'm happy to share, but maybe not.
Yes,